In this video, we will compute the surface area of a surface defined parametrically. So first, let's recall the general formula. So for a parametric surface, given as a function of two variables, a vector valued function, with uv in a parameter domain D, so D is some region of the uv plane, then the surface area is the integral over D of the length of a certain vector. And that vector is the cross product of RU and RV, where RU and RV are the vectors of partial derivatives of the original parametric function in terms of the variables u and v. So this is what we'll use in this problem. Okay. So now for this specific example. So we're to compute the area of part of the sphere of radius 1, which lies below the cone z is square root of x squared plus y squared. So here's the cone. So we want the rest of the sphere minus the little bit that's above this cone. So the first thing we need to do is parameterize this piece of the sphere. Since it wasn't given to us, we have to come up with it. But this is easy for pieces of a sphere. We just use the spherical coordinate equations. So let's parameterize the surface. Instead of u and v, I'm going to call them theta and phi, like the variables used in spherical coordinates. So remember, in spherical coordinates, x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. So I left out the rho because we're on the unit sphere, so here rho is always equal to 1. So when we parameterize a piece of a sphere, you just use the spherical coordinate equations, but set rho equal to some constant, whatever the radius of the sphere is, in this case 1. And we need bounds for theta and phi. So theta goes all the way around. But phi does not. So we're leaving out the top part of the sphere. Now if you think back to spherical coordinates and figure out what the equation for this cone is, it's exactly phi equals pi over 4. And so that will be the lower bound for phi, since we don't want anything above the cone. So phi will start at pi over 4, and it will go all the way down to the bottom, which is pi. Okay, so this is our parameterization of the surface. If you remember from the general formula that I wrote down earlier, we need to take partial derivatives of this, take their cross product, and find the length of that vector. So we have to do all of this before we can compute the integral. So first, let's compute these two vectors. So first let's take the partial derivatives with respect to phi. So first we get cosine phi, cosine theta, cosine phi, sine theta, and minus sine phi. And now if we do theta, we get minus sine phi, sine theta, sine phi, cosine theta, and 0 since there's no theta in the third slot. Now we need to take their cross product. The order really doesn't matter here. If we remember from how the cross product works, if we flip the order, we just get a minus sign on everything. But we're going to end up just computing the length of this vector, so the minus sign will be irrelevant. So I'm only choosing this order to minimize the number of minus signs that we get. So if you compute this cross product, we get sine squared phi cosine theta, sine squared phi sine theta, and cosine phi sine phi. I'll leave the cross product computation to you. And now we need to compute the length of this vector. So this is the square root of, and we square everything and add it up. So sine to the fourth phi cosine squared theta plus sine to the fourth phi sine squared theta plus cosine squared phi sine squared phi. So let's simplify. This looks kind of ugly, but it turns out to be very simple once we use a couple trig identities. So let's factor out this sine to the fourth. And what's left is cosine squared theta plus sine squared theta. Which we all know is just equal to 1. So that makes things simple. And we can simplify yet again. We have a sine squared here and a sine squared here, which we can factor out. And if we factored out of the first term, we're still left with 2 factors of sine phi. And in the second term, we're left with cosine squared phi. And again, using the exact same trig identity, this part in parentheses is just equal to 1. And so we just have square root of sine squared, which is sine phi. Technically, it should be absolute value of sine phi, since we're taking the square root of something squared. But if you remember from spherical coordinates, phi is always between 0 and pi, so since it's always going to be positive anyways, we don't really need the absolute value signs. Okay, so we did all this work, now let's use the general formula. So we need to integrate over this region this function, which just turned out to be sine theta. So the surface area is the integral, and we had theta from 0 to 2 pi and phi from pi over 4 to pi, and the function just turned out to be sine of phi. There's no theta in the function, so the first integral just gives us a factor of 2 pi. And now the integral of sine is minus cosine. But instead of putting the minus sign there, I'm just going to flip the bounds on the integral. So instead of going from pi over 4 to pi, I'll just go from pi to pi over 4. And that'll cancel the minus sign that we get. So this is 2 pi times cosine of pi over 4 is 1 over the square root of 2 minus cosine of pi is negative 1. So this is plus 1. And there we have it. This is the area of that piece of the sphere.